This is lesson 56 of the Quantum Mechanics mini lecture series titled Operators Part 1. So, as I mentioned before, the stretching of a vector, okay, so let's suppose I have a vector v, okay, which looks like this in column form. The operation of stretching this vector along, let's say, a particular direction causes its length to become doubled. If I do this, let's say, if I multiply this vector by 2, I'm doubling its length basically. This is actually called, this can be expressed as an operator. I can express this process in the form of an operator. So in more general terms, an operator O, okay, turns a particular vector v, okay, so an operator O acts on the vector v to give you some multiple, let's call it lambda, of itself, v. Okay, O is for operator, v is the vector, lambda, okay, this is the Greek symbol lambda, okay, it's some number, it's a constant, okay, and v is the vector. So accordingly, the vector v is said to be an eigenvector. It's given the fancy name eigenvector. It's the eigenvector of the operator O. Okay, and lambda is the eigenvalue of the operator O. Okay, eigenvector, so vector because v is a vector, eigenvalue because lambda is a value, it's a number. And in quantum mechanics, the eigenvector is also synonymous with the term eigenstate. Okay, an eigenstate will correspond to a physical state which measuring the observable quantity O will, with certainty, will give you the result lambda. So the operator is some measurable quantity in quantum mechanics. A measurable process, I should say. Okay, also known as an observable. An operator is basically a mathematical object that acts on a state vector. Okay, and in this case, the vector becomes state vector. So O acts on the state vector V. Okay, and the state vector is a vector describing the state of the quantum system. Okay, so it'll change it to some other vector, V. So operators are always represented by a symbol with a hat on top. For example, X hat. So this is the position operator. Okay, position is typically given the symbol X. Operator is given the hat symbol. Okay, operator. In general terms, an operator looks like this mathematically. Okay, so it basically maps some state, psi, to another state, phi. This is the Greek symbol phi. Okay, and in quantum mechanics, operators have the property of being linear. Okay, this means that some operator O acting on, suppose I have these two states, okay, with eigenvalue, with coefficients x and y. This means that you take out the x, operator O acts on the individual states, plus y. Operator O, psi 2. Okay, so you pull out the constants, x and y are the constants, and the operator acts on the individual states. Okay. And generally speaking, x and y are typically complex numbers in quantum mechanics. Complex numbers. And so we conclude that the new state, phi, is a multiple of the original state. Okay, in other words, the physical state of the system hasn't changed, but rather something has been done to it. And note that operators always act to the left of a state. You can never have something like this. That's not allowed. You can only have something like this. Okay, operators act on the left. As an exercise, try and show that the operator A, some operator A hat, acts linearly on the quantum state psi is equal to A0 plus B1. Okay, the same thing that I did here before, showing the linearity, can't even pronounce it, linearity test. And in the next video, I'll show you how operators can be represented using matrices. But that's the idea of an operator. It's something, some action on a quantum state which maps it to some other state. Okay, it's like a machine, if you wish.